All right, are we live? Let's see. Hello, 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 hello. Looks like we are. Very good. What's up, stream? Hello, world. Hope everybody's doing okay. Very good. I'm gonna go ahead and oops. Oh no. Ah. Um. Okay. And oh, I feel like people liked my comment. Hey, you got some retweets. Sweet. I mean, not that it's not for me. I mean, never mind. I like getting retweeted, but it's not. It's not. What do you call that? Never mind. I just Jesus Christ is Lord is trending on Twitter. It's awesome, and I commented on that. That's all. That's all. I like getting retweeted, but obviously it's especially something like that. Like it's not for me. All glory to God. All glory to God. All right. Contains duplicate. Given an array of integers, find out whether there are two distinct indices I and j in the array such that the absolute difference between nums I and nums j is at most t, and the absolute difference between I and j is at most k. Okay, this is interesting. So, whether there are two distinct indices such that the absolute difference between them... Oh, that's interesting. The absolute difference between the values in the array is at most t, and the absolute difference between the indices is at most k. Interesting. So they're not further apart than k, and the values themselves, the absolute difference is at most t. Pretty interesting question. I don't know the solution offhand. I think you can do this in linear time, probably. So give some examples. I have to kind of think about this some more. So if k is 3, excuse me. So the absolute difference here is not that significant because that basically just means that you throw out any, you can just filter on any possible solutions and remove the any solutions that are further apart than k, the indices. So it's not really, and you're just trying to figure out if it's true or false, right? So you just need one possible solution, one possibility here. So I mean, there's at least two different. So there's like, okay, a naive approach would be to take all of the possible pairs of indices that are at most k difference between them, and of all those pairs, check for this condition, and then take the absolute difference and see, check on every single pair if that absolute difference is less than or equal to t. And if you have anything left over, it's return true. So that naive approach would be quadratic, at least, because there are a quadratic number of indices, of pairs of indices, I and j, and with quadratic with respect to the input. And yeah, I'm pretty sure you would just, each of these operations would be linear with regard to the number of pairs, so it would be quadratic operations over and over again. It's not very good, but it's one way of doing it. And we want to go for at least linear or like log linear type of algorithm. Also, we have some other pieces here, and Finding that the absolute difference is at most t. If you're looking to, let me think. You can do some sorting here. Oh yeah, that's interesting. So if you sort the list, that'll give you the minimum differences. So that every number, the numbers to the left and to the right, those two numbers will be the minimally closest numbers in terms of distance, right? Sort of by definition of sorting, right? So if you take some index x or index I, and in a sorted list, if you sort all these numbers, you find some index I, the number to the left and the number to the right. Those are the two numbers closest or have the minimal absolute difference. One being the minimum and the other being the penultimately minimal difference, because the numbers to the next number to the right or the next number to the left would be further away by definition, right? Or if there's no duplicates. If there's duplicate values, then they're obviously they can only increase. It's either greater than or equal to in terms of difference, right? So it could be like the same number repeated again, but just keep going until you find a number that is sort of large enough, I suppose. So what you can do is sort the numbers, and then you just maintain a hash of where the indices are for each of those numbers, where they were originally. And then what you can do is, because you know what the that one of those two is the minimal difference, you can do comparisons, sort of left to right. You can iterate over the array and do a comparison of the left and right numbers, and check if they fit this criteria, right? If the absolute difference is less than or equal to t. And if it's true, then you can then check the second criteria and you can use the hash set that you stored before, the hash map you stored before, to get the indices and check those indices against each other. You actually don't even need to, because you're going left to right overall, you're iterating over all the elements, or whatever. It doesn't have to be left to right, but because you're iterating over all the elements, you actually don't need to check the left and right pairs of each element, because if you think about it, you're going to check the left and right pair of the first element. Obviously, there's no left pair. And then the second element, you've already checked the left and right, the left pair of this element, right? Because that was the previous element's left and right, if you're going left to right through the elements. Hopefully that made some sense, that sentence. So you'd have A and B. You have already checked this condition on A and B. And then when you check B, you don't have to check it against A again. You can just check it against C. So you can sort the list and just go left to right, checking the differences. If the absolute difference is less than or equal to t. And then if it's true, then you can check, you can use your unordered map. You can use your hash map to get the indices and check the indices against it. This is a pretty straightforward question. I think, yeah, this is basically you sort it first, then you check. In your sorting, though, you want to store the values indices. What you might want to do is actually create so one approach would be to actually create tuples of the value in the index, right? So these are sort of paired off values, and then sort on the first value of the pair. So that way you sort you don't lose the index, and then you don't actually need to use a hash map. The index is just sort of already there for the pairs, because then you can do comparisons between the pairs. That might look something like that. And you can use a custom comparator for the sorting. So let's try to do that. Let's see if we can do that. So let's do standard vector of, and also this is going to be const reference. Standard vector of tuple, and it's going to be int, and we're going to say val index pair tuples, val index tuples, and we're going to say for auto x in, oh no, let's do it this way. You can actually use iterators too. I kind of would like to, I want to try that out. Nums.begin of it not equal to nums.end plus it. And we'll say int index equals iterator minus nums.begin. You actually can do, yeah, you can actually do it that way. It's kind of interesting. And then we're going to say val index tuples dot pushback standard make tuple, or like, yeah, make tuple. Okay, sure. And we'll say the value, which is in the index. And then now we want to do standard sort on val index tuples begin and val index tuples end. And we want to use a custom comparator, a lambda function here, which I'm not sure, I might want to do it this way, auto sort on first. Kind of would prefer to do it this way. Sort on first. We'll say custom sorting. Compare, yeah, it's comparator. Comparison function, object that satisfies the requirements of compare, which returns true if the first argument is less than const type comp boolean signature should be equal to the following. Signature does not need to have const. Function must not modify the object. So we're going to get the first. We're going to use this this lambda expression, and it's going to be const standard tuple of int reference a, and then same thing here, const standard tuple of int b reference b, and basically we say a dot return a dot, so the sorting, yeah, a dot first I want to say, or how do you access tuple access in cpref? I think it's a get. I think that's what you use. It's like a, yeah, get standard tuple, yeah. It's actually a standard get a, and then I want to say use 1, yeah, 0, 1, right? So 0 is what we want to use. Kind of interesting. Is less than standard get of 0 of b. Yeah, that's fine. So sort on first. I'm going to say ascending. And hopefully that does what we want. And then now we can loop p each of these tuples, or t in val index tuples. Actually, you do want sort of to do this using an iterator, I guess. Auto it equals val index tuples dot begin. It is not equal to val index I'll do auto begin equals, and then auto end. Just so I don't have to type so much. It's kind of a lot of typing when you do this. And you can do it plus 1 instead of doing n minus 1. And so we'll say by the way, also we can do if it has one element, then it plus 1 is already the end. It'll exit. So we'll just say sanity check if num's empty, or if num's empty, rather, just return false. Or nums.size is less than, you don't actually need this one, but less than or equal to 1. I guess it's kind of the same thing, nums.size, nums empty, something like this. Just say nums.size less than or equal to 1. Sanity check here. And we can do the other ones too, or, you know, k is, we don't really need to do that. I was gonna say if k is negative, however, you'll just always return false if k and t are negative, right? Because these will just never be true. Neither of those will ever be true. Okay, so next is going to be it plus 1, and we want to say int diff is going to be it minus next absolute value. And then we say if the difference is less than or equal to, now here's the thing, right? We need val1 to be standard get 0 of it, and val2 to be standard get 0 of it, or of next. And there we go. Now we have the val1 minus val2. That's what we want. Now if the difference is less than or equal to, we said t, and then we can say and the, well, I mean, I wonder if we can do this. I'm kind of curious. Auto v1 i1 equals it and auto v2 i2. I want to try something like this. I could do val1 index. We do val. And then index. Could be a little more descriptive, right? So the difference, and we can do difference 1 and difference 2. Could just do these in the same routine, why not? So, okay, that's the only, you just return true immediately if that's the case. Difference 2, yeah, I and j is k, all right, the indices. So let's see how this is what happens here. Oh, it worked. Sweet. Compiled and everything. Everything worked. Awesome. Nice. Glad to see that. I like that. 1 0 1 1 1 2 1 5 9 1 5. The power of using auto. Let's try it instead of trying to figure out the templates yourself. Allows you to very quickly code it up without too many errors. Oh, pretty nifty that this actually worked. This whole setup. Can actually get rid of this next 2 and even do it plus 1. Same thing. And let's do empty 1 2. Should get a failing test case or something. No. Okay. 1 2 1 1. Okay, if we do just 1 in there, 1 1 1. Okay, and I don't know, could we just do some random numbers here, I guess? Random inputs. Num's length is 20,000. The numbers are, I can have negative numbers in there. So just throw some negative numbers in here. And K could be 10,000. T could be very large. Excuse me. All right, it's pretty convincing. It's possible that I missed something somewhere. It'll come out in the test case or test cases. I mean, I'm really tempted to just give it a shot, you know. Yeah, let's give it a shot. My algorithm could be wrong, although I don't think so. Let's go for it. Oh no, we have a runtime error. Oh no. Yeah, I often don't consider those cases where you have really large numbers. I forgot about that. Yeah, I should have. Oh man, I always forget those. Overflow errors. It's kind of a really obnoxious reason to fail on a test case, just due to overflow. Like these are errors that you wouldn't see if you were using something like Python, because Python automatically has big integers. Every integer is automatically what's the word? Arbitrary precision. So it'll handle all this stuff, but this stuff doesn't get handled nicely in C++. You have to kind of explicitly handle it. Yeah, because the absolute value of the difference between these two is no longer going to be. Yeah, this difference could be a long now. I mean, okay, I guess. Overflow. Oh. Okay. You just have to upgrade one to a long, and the other one gets upgraded automatically. I mean, I don't know. Can the indices be? No, the indexes can't be. The numbers themselves, the difference between the numbers could be a long. And is that it? Is that sufficient? Wrong answer. Shucks. All right, so I was just wrong. I'm sad now. Disappointed. I thought I was so slick, man. I thought I did such a good job. 1362. Why would that be wrong? False, expected true. Okay, why though? Okay, unless I confused T and K, which I could have done that. K is the indices, and T is the value. Okay, so 1, 3, 6, and 2. And which one comes first? K comes first, T comes second. So K is, all right, so they got to be at most a difference of 1, and T is the difference, absolute difference at most T. So here, absolute difference is 2, so this should be true. Absolute difference is 3, absolute difference is 4. All right, let's print these differences then and see what we get, what happens. So this actually, the algorithm should return true here, so it's a little strange as to what's going on. The algorithm is right for this test case, or should be right for this test case. I don't know what, maybe somehow I coded it up, it came out wrong. 1, 1, 3. Value 1, value 2. Oh no, you're kidding. Oh, it's wrong. The algorithm is wrong. Because, oh no. Oh, you're kidding. Oh wow. Oh, I'm a dummy. No, because you're only checking the absolutely minimal difference here. However, there could be something a little further away. Excuse me, you could have something that's slightly larger value here, but it's closer here. So it satisfies this condition. Oh no! Oh, I screwed up. Whoops. Whoops. Big mistake. Oh, that's bad. Oh, that's really bad. Gosh, and the algorithm is wrong. I thought it was so clever. I thought it was so clever. Gotta be careful when you have two conditions. You gotta be careful. You don't necessarily want to minimize on one of the conditions. That could be wrong if you do it that way. And only consider the minimal here. It doesn't have to be minimal. It could be just, it just has to be a most T, so. There could be a few possibilities. So if you just check one, it's definitely not right. About that. Okay. So what's interesting about this though, is I think you can use roughly the same algorithm, same sort of running time, almost the same running time. The only difference here is, where's K? Yeah, you just have an additional K term in here. Really it'd be the same running time because K has got to be less than or equal to the length of the array anyway, O of n anyway. So K is bounded by O of n. So if you add an extra O of n, it's still going to be n log n, just weighted by the sorting time. What I think needs to be done is actually you have something what you do is you check from left to right on the first index until this condition, this absolute difference, is no longer holds, right, left to right, or yeah, I think that's it. Actually, you just keep checking until it no longer holds. And actually, do you even need to do it this way? Yeah, maybe you don't even need to sort it then if you do it this way. Alternatively, you can just check from left to right the K. I'm actually not sure now. I can think about it. What I'm thinking is, all right, let's start with the first thing. So you check from left to right, and you find until this is no longer true. And on each of those, you perform this check for I and j. And then on the next value, you don't need to check the next index. You don't have to check the previous index because you already did that. And all of those differences that you just looked at, they're all going to be satisfied for this next value. So then you can start looking further ahead up the chain. However, the index might be different though. So you might want to check all the indices. Try not to get, oh no, man, I don't know. This is a tricky problem, man. This is a tricky one. I screwed up. I got it wrong. Wrong algorithm. Ouch. Yeah, because no, because the indices could be different. If the new index is further away than the previous index, then you don't have to check those things. But if it's closer, then I think what you ought to do, you just have to keep track of the minimum index or the minimum difference, right? If one of those indices that you just checked, if that difference, that absolute value of the difference is you actually don't even, it's not even the absolute value you want. You want the oh gosh. Oh no. You still have to be careful because you're looking for the absolute value of the differences, so it's got to be some of these differences I guess what you're going to want to do is find the maximum and the minimum difference, or rather the smallest positive difference and the largest negative difference, right? Those two numbers you want to keep track of. And then when you shift the index, change the index of those values, whatever the difference is between the indices now becomes the difference over those minimum and maximums, right? So you just subtract on those two. And if the absolute value of that difference that you just subtracted is now within range, then you can just return true. You don't have to continue your algorithm. However, if it's not in range, if these things are not in range, then you don't need to consider any of those numbers, right? Because you already checked them. You didn't necessarily already check them, because it also depends, right? Well, now because you're sorted, now you're closer to this absolute difference. Yeah, this absolute difference should be now even smaller. Yeah, so you don't have to check those for this condition, but you do have to check them for for this condition, this absolute difference, which actually you can do in constant time. So actually, yes, you could still do a modified version of this algorithm. However, it's a little bit more complicated, I believe. It's kind of funky, but let me see if I can draw it out or write it out. Yeah, okay. I can save that. Oh man, I can't believe I got this wrong. I feel so, I screwed up. Let me just code it out. Well, like 1, 2, 3, 4, right? And these have some indices. We'll call them just, 0, 3, 1, 2, right? Something like that. What you're going to want to do is you compare to the right until, let's say all of these passed the checks. And then you say, okay, there's the indices. So really, because you could have like 2 as the index here, and then let's put the 0 over there. What you want is so 2 minus 3 is -1, 2 minus 1 is 1, 2 minus 0 is 2, right? The smallest positive is 1, and the largest negative is -1. You want to keep track of those 2 values over those those differences as you compute these things, as you check. And then you want to say, okay, when you look at the next index here, you're going to update. So 2 minus 3 gives you -1. Oops. Gives you -1. And so all of these differences in indices, right? And so all of these values, 2 to 3, 2 to 4, because 2 is incremented, you're only going to get closer to these values, right? We know that, so we don't have to check them again. So now we have our sort of our pointer over here, and then we say, okay, take this -1 and add that to everything else. So you get -2, 0, 1. Really don't have to add it to everything else. You just have to add it to the least negative and the most positive, or the least positive and the most negative, or excuse me, least negative and least positive values. The largest negative value and the smallest positive value. And if you add that difference, then I think you actually subtract that difference, by the way, not add it. You subtract it. So this 3 minus 1 actually, so you subtract, so you actually end up adding 1 to everything. Right, which I think is correct. So this becomes 3, this becomes 2, this becomes add 1, you get 0. Which is true, right? So 3 minus. Now the question is, oh, now you have a problem though, because if that minimal value that you just looked at happened to be this pair, one of these minimal values happened to be that pair, and then now you just clobbered it, excuse me, by basically taking this index back to itself, then you're in a bit of a tricky position, aren't you? Because then you need to know what the other previous value was or is. Oh no, man! Oh no! That's interesting. You can kind of keep the numbers in a heap, something like that, I guess. Although there's no real point to that. Yeah, you know what you want to do? You just don't want to keep track of the previous value. That's all. You just consider all the other values, and you don't consider that one at all. You skip that one because yeah, when you're considering the minimum, the largest negative number and the smallest positive number, when you're keeping track of those things, don't pay attention to when you are keeping track of those things. Don't even consider this first pair. Basically, skip this first pair. Pretty much. That's pretty much the way to do it. The problem with that, though, is that on the next iteration, no, that doesn't work either. That also is awkward. No, that doesn't make sense either. Because let's say you move over now, right? Now you have this pair and this pair. And let's say this one was now the maximum or minimum, whatever. It's going to get removed in just a moment. It's going to get removed once this gets moved over next time anyway. And now you're in the same position anyway, so you can't just do one element. Oh gosh, I think you do need to have them all in like a heap, which is very awkward. Which is awkward. You could potentially keep them in a in two sorted sets. One of them sorted in ascending order, one of them in descending order. And that's kind of the same thing as the same idea as the heap. And what you would do is, I guess you have something of like a modifier that gets applied at each step to consider the values in the set, and that modifier is the sort of the difference in indices as you're walking through the sorted list from left to right. I think I'm making this algorithm a lot more complicated than it needs to be, by the way. I think there's a sneaking suspicion I have that I'm like trying to force something where like I'm trying to do this thing using sorting, and I maybe I could be doing this without even using sorting in the first place. Like I want to say something, I could do something with like a stack or a set or a heap or something, and I probably don't even need to use sorting at all. Let me think about that. Because it's already sorted by indices. So you can kind of perform this check from left to right on the first k indices, right? The first value, the first index compared to the next k indices, and then when you go to the next index, you don't have to look back. You have to look. You still definitely have to look forward to the next pair, but you also comparing between these other pairs. Well, that would give you k times n, a k times n algorithm, which I think is too expensive, right? I think k times n gives you sort of quadratic time. So I think you do have to do some shenanigans with sorting. I kind of like this approach. that I'm describing. I think it's okay. Huh. It is n log n time. So, but it is kind of funky. Yeah, because you get this like k log k sort of thing going on where you're no, it's just another n log n thing, right? Each time you I guess each time you maneuver over to the right, you have to delete from the set that I guess that difference in indices or something. I don't really even know. I don't know how to do that either. I don't know if you want to use a set necessarily for that either. You kind of want to remove. Oh gosh. Oh no. This is so tricky. This is so tricky. Because the problem with that is maybe better would be to check, you know what would be better? I know what to do. Okay, you have a set of indices that you've looked at so far. Do it that way, right? And that's sorted in either ascending or descending order, right? And then you have this value that you compare against the front of both of those sets, right? And if you are in range, then you return true. If you're not, then what you're going to do is remove the next index from those sets, right? Do a removal, and actually make that the next value to compare against, and then also add any more indices that you need to add based off of what's actually at what that actual value is. So you can extend this set further to the right. And now here's a question. You don't, you don't, okay, I think I got it. All right. This is an interesting question. It's definitely an interesting question. Definitely an interesting solution. I like this question. This is good. It's kind of a funky approach, but I think I got it. I did this wrong. I was so wrong. But yeah, what you're going to want to do is you keep two sets of indices you've already passed through. And you're still going to go through pairs, right? You're going to iterate over these pairs. You're going to iterate over the whole thing from left to right, and you're going to keep another pointer that's just ahead. And what you're going to do is the first value, initially your first value, the pointer that you're pointing to is sort of the value you're interested in, that index, and the value. And you're going to populate these two sets with. You're going to consider the values and the indices, and you're going to dump all the indices in these two sets of ascending indices and descending indices, and then also check the value against sort of the value that you're pointing to, right? And then you're going to stop when it's no longer, the first condition is no longer true. So when the difference between those values is too large. And then once you've updated the set, then you're going to check the absolute difference between the index and the front of these two sets, the ascending and descending. You actually could even keep it in one set and just have keep it in one set and just have a hold on, I'm just thinking. I'm actually not sure if that's right either. Oh no. No, you know what you gotta do? This is so awkward. But I think I'm on the right track, but it's okay. Actually, what you need to do is forget what I was just suggesting with ascending and descending and all of that. You do a search for this index in the indices that you just looked through. do a search for this value in the indices that we just searched, we just put in there into a set, and find the two indices that are closest to it, and then do a comparison between those two. The two indices that satisfy the first condition, and then they're also two closest to this value, and then they might satisfy the second condition. Yeah, and then you can remove the next index. You're going to remove it from the set when you consider and add the other indices too. Add new indices. Oh man, super interesting question. Really interesting question. Wow. Wow. I think that works like that. It's pretty complicated, the algorithm as described. It's kind of a lot of pieces going on here. I think I got it though. Gee. Okay, so all right, let's start with populating the algorithm that's going to populate this set with new values. Let's start with that piece. So that's sort of the first part. Is we have two iterators. We're gonna have a beginning. We're gonna go. It's actually gonna go to the end. This iterator, and then we have a second iterator, it too, or just like next, which is gonna be it plus one, or begin plus one, right? And we're going to say, we're going to do a for loop for, or just a while loop, while, even, while. This is just a true. We're going to have this set also of values. We're going to say indices, valid indices, possible indices. Say valid indices, valid indices. Possible index. Yeah, we'll just say possible indices. Do it that way. And so say we're just going to say while true. Let's say auto next val next index equals next pointer dereferenced, and then we say okay, this difference is going to be the absolute value of, we can say auto val index equals dereference iterator. Difference, the absolute value of the value and the next value, and we'll say if difference is less than or equal to k, then push into possible indices, insert this next index. And then you say otherwise, and then we say else, break, right? And while we'll say next is not equal to end. And we kind of want to do a for loop here, really. And we're going to increment next. So we're going to loop until this breaking condition, right? And so now we know that everything in possible indices is those are all indices that could be paired with the current index, with this current index, right? Now what we want to do is first we want to check if the index is in, there. So just say if index, so it's really, I think it's find, I guess. How would we express that? So you do if possible indices dot, it's really, yeah, find or contains or count, I think count of index. If that's non-zero, then we're going to do possible indices, remove the previous, or remove the current index from the set of considerations. It's still there if it's there. Right, obviously the first index won't be there, but the other ones should be. Dot remove, erase index, and then find the nearest neighbor indices to the index, current index. A set of possible indices to consider. So this is going to be standard, I think, lower bound we want probably. So not less than or greater than or equal to. It doesn't really matter greater than or equal. We're just going to do, so I just want to know if it's greater. So what we're going to look for is the first value that's greater, which it's got to be greater because there's no duplicates with the indices, right? The indices are a one-to-one function, right? By definition. So the lower bound of possible indices begin. I almost want to like give this a different name because it's kind of a mouthful to keep typing. And then we want no, not that one. Man, I can't believe I messed this up. We want the begin, the end, and the value itself is the index, right? And we'll call that auto greater, right? And then now we're going to say if greater is not equal to end. So we could do if greater is not equal to begin, or which is just possible indices at begin. Then we could say lesser. We'll set the lesser to be the end, right? So it's going to be possible indices. We can just say if it's not greater than the beginning, it's not the beginning, then we'll say lesser. Can do it this way. We just set them to point to the same thing. It's going to be greater -1. And then it really should be null pointer, I think. Yeah, we can do, yeah, there's a greater and there's a lesser. Just thinking how to do this. The greater could be the end, right? It could be right off the edge, in which case lesser exists. But greater could also be the beginning, in which case lesser doesn't exist. Yeah, that's what the edge case I'm trying to check for. So let's do it this way. Let's say if, and then we're gonna do int check val. So let's do it this way. So if greater equals the beginning, then we're going to check return the standard absolute value. I don't know. Let's do the difference or long, or just this one could be yeah, diff. You know what we'll do? We'll do it this way. K plus 1. Let's put diff at k plus 1 initially, so it's initially false. So if greater is equal to the possible index begin, then we'll set diff equal to the standard, the absolute value of the difference between greater as a value minus the index. So if it's the beginning, that's just what the difference is. Otherwise, if greater is equal to possible indices dot end, so what I'm trying to show is greater is the beginning, then there is no lesser, so we only consider one pair. If the greater is the end, then we're going to take the difference between greater minus 1 minus the index, because greater doesn't even exist, and then otherwise we take the difference to be the minimum of these two things. This one and the other. And just keep things kind of clean. Int d1 is and d2. Oh. Yeah, it's pretty funky kind of way to do this, kind of wonky. A whole lot of wonk going on here, but I wasn't really sure how to articulate that cleanly and simply. It's kind of hard to do. But yeah, so you find something that's greater than, and then the value you're looking for, the index of the thing that's greater than, and if it's off the edge, that means the thing to the left is going to be the maximal value, right? So being off the edge is here, and so that's the only pair to check on the left side. And then if you're on the furthest to the left, you're at the beginning, then the only thing to check is the greater itself against the index, right? There is no smaller value. And then if you're somewhere in the middle, which is obviously neither of these two cases, that means there's a value to the left and to the right. And so you can take the greater and then take greater minus 1 and consider those two independently and take the minimum of those differences, absolute differences. And then you'll say if diff is less than or equal to k, then you return true. And that really should be it. And in all of the cases, return false. So, right, if you never return true, then you return false. So we have to just double check. You have your tuples, you have your indices, and you're going to say if next is not the end, then you're going to basically keep considering values to place into this set of possible indices. And you have this difference of the values themselves. So as long as those differences are less than t, not k, less than or equal to t, then you can keep adding these indices and then go to the next thing to consider. And you'll hit a point where you're either at the end or you're either at the end or you actually, yeah, it really should be it as you hit the end, should be. Or there just aren't any more values that are sufficient. Because this is sorted, you kind of should always have. Now I'm wondering if like you have a case where the values are like really far from each other in some cases, where it like just kind of breaks apart for a moment. Just thinking, you actually never update this to your current position. There is a case where this can get kind of funky. You kind of just keep getting stopped at a certain point where this is always not true, and you just keep breaking here until basically this iterator catches up with this iterator. In that case, once they're on top of each other, what do you do? Like, it's fine when they're not on top of each other, but once they're equal to each other, then what's happening is you would have to say, so if it is on top of next, then you have to say next plus equals 1. And you also have, now here's the thing, you're not going to add, you can also just throw this in here too. You can say and you can also do next equals begin too. You don't need this here in here anymore, right? Because it'll be automatically be pushed forward here. You're not going to add into your list of potential indices ever the value you're currently considering, right? Like you're considering sort of index pairs. So this index could always just be pushed forward, right? So let's say you kind of like they basically meet, then you move this next forward, and I think that's all you got to do. Nice. Greater minus 1 minus index. Excuse me? No known conversion from big iterator base first argument. Oh no, please no. Huh. I think the problem is when you're dealing with a set, you can't just subtract. I think might be the issue. Yeah, okay. Auto temp, call that standard advance temp equals greater. Actually, yeah, you can do better than that. You can do standard advance greater minus 1. And here you would do D2 first, or D1 first, and then standard advance greater minus 1. Yeah, I think that's the issue, because you're using it's a logarithmic. It's not. You have to advance the pointer correctly. Oh, okay, it worked. Sweet. How did we do? Runtime error. Sweet. Nice. Shouldn't have runtime errors for the indices, but you might have runtime errors for. Oh yeah, gotcha. Forgot that again. Wrong. Nice. Okay, what do we get wrong? Please tell me my algorithm's not wrong again. I'll be so sad. I spent so much time thinking about working on this one. What's the difference between these two? True, true, false, false, true, false, true, true, false, false, true, false, true, true, true. False. So it's this case, the second to last case down at the end here. Which one is that? It's this one. It's exactly this case. Really? Really? Wrong. It's output true, expected false. Why? If you take this difference, take the absolute value, and so you have the first, this index, the value index, this negative thing, and then you say, okay, next value, next index, right, of this next, right, this iterator starts at the same point, goes to the next one. It's not equal to the end. You say, okay, take this difference, and you say if this difference is less than or equal to t, which is false, then you insert into these possible indices. So difference is t. This is going to be false, right? T is small, so this is just break. So you don't have anything in these possible indices. So there's indexes there. You're going to erase it. It's not there. This is going to be index lower bound. It's going to end up being. I don't really know where this ends up going. Probably the end, I guess. There's nothing in there, and then you advance. Oh, I see. This difference is just like a random value. So if you don't have any values left to consider, like the no possible indices left to consider, that's sort of at the very end. Because this could return true in this case, right? I'm just thinking if this case could happen again in another circumstance, another index, like another circumstance, or when you get right to the end, and let's say you're kind of approaching the end to return false. The last, you're kind of removing stuff. Yeah, the indices are being emptied. The last two values, you have maybe you have one index left in there. You perform this works correctly, and then you're on the last value, and actually this needs to be excuse me, this can be this can actually be stopped here. Oops, what did I just do? Should this be stopped here? I want to say you could just stop it right here. Yeah, yeah, that's fine. So this won't iterate on the very last element. There's no need to. There's no reason to, because there's nothing to the right of it anyway. So, but still, in this case, what happens? You have, if this is empty, for whatever reason, then its difference is going to be kind of just like random gibberish, basically. Yeah. It's basically this will grab random gibberish in the case that this is empty. You could probably, a better thing to do would probably to put the whole thing in this block, this entire thing in a large block. Yeah, because this doesn't really handle that case. None of these cases really handle that. Yeah. Okay. So these test cases then. So that's pretty good. I'm afraid to hit the submit button. I'm scared. I don't know. I'm going to go for it. I don't know what the test case I could have missed. I don't know. I don't know, man. It's either the wrong algorithm or there's some test case that I missed. I'm afraid to hit the button, but I'm going to go for it. Hey, we got it. Okay. All right. Gee. Oh, man. Ouch. Ouch. That was brutal. Dude, I got destroyed by this problem. I got annihilated. I don't really know, man. That was an interesting one. That was definitely an interesting one. I don't know what to say. Maybe we'll look at the discussion, I guess. We could look at the discussion and see what people have to say about it. Dude, I got annihilated. How long have I been doing this? Looks like I was here for almost an hour. Yeah, over an hour on this one. Oh, gosh. It's rough. That's rough, man. That's rough. Gee. All right, what do some of the discussions say? Java tree set short concise O of n. I don't think so. Brute force tree set O of n log k. Easy Python solution. Second test case. So the problem resulting in TLEs and log k, I think. C++ 14 solution. I had n log n. Sliding window of n log k. Contains nearby almost duplicate. K log k space O of k, creating a balanced BST of k numbers and deleting inserting k minus k numbers in a balanced BST of k numbers. Contains nearby almost duplicate. K is less than or equal to 0, return false. If k is greater than or equal to the number's size, k equals num size minus 1. I mean, okay, I guess. What is k? Yeah, k is the... Does it really matter? Oh, I see. Yeah, I think I understand why, right? Because you do a loop over k instead of looping over... I think I understand. Not sure exactly why I did this, but this is a set. I equals 0 nums dot size of I plus plus. So these are the indices. If I is greater than k, you can erase I is greater than k, erase I minus k minus 1. Oh, that's why I wanted to use. Okay, I see. That's why. I guess you're assuming that the array doesn't have duplicates though in this approach. That's the thing that I'm kind of, I don't know if the problem actually said. I don't think the problem actually said that there couldn't be duplicates in the array. Nums position 1 lower bound nums I minus t condition 1 position 2 condition 2 above line and corresponding condition below are commented because they're not required. Range n minus t n plus t if a number greater than or equal to n minus t is found. And set and it satisfies absolute difference in check. We don't need to separately check. I'm not really sure. Position 1 is not equal to the end, and the absolute value of the difference between these is less than or equal to t. You don't need to check that either. Return true. Insert this nums of I into S. Huh. Interesting. So okay, so I think this, what I think this is it's a sliding window of the numbers that are, I guess, to the right of k, or to the right of I. Okay, interesting. So I think it's a sliding, he's building the sliding window as he goes from left to right. And so the initial value is I is greater than, it's not greater than k, right? Assuming k is non-zero, is at least 1, right? Position 1 is you look in your sliding window and you find nums of I minus t. So this value you're looking at currently minus t, right? That whatever that difference is, take this position, take the lower bound. So it's going to be the first value that's greater than this difference. So when you subtract t, so this is a sliding window. You subtract t from the value you're currently looking at. If it's negative, then you're going to look at the very beginning. I'm not really sure. This is kind of an interesting way to do this. I guess the sliding window, the numbers in the sliding window, you take the current number you're looking at, which is going to be to the right, some random number to the right, subtract from that number t, so that's the difference between this number and t, and then check in your sliding window. And I'm not sure what's being put in the sliding window. Yeah, it looks like just the numbers are being put in the sliding window. Everything to the left. There's some position. So what I guess you're trying to go for is like, this is kind of tricky. I wouldn't actually guess this offhand. What I want to say is, yeah, he's saying, okay, basically there could be two conditions where you say subtract t or add t, right, from the number you're looking at, and then check in this set of values where you might find the other. Oh, okay, I see what he did. And then he's saying, well, you don't actually have to do this check anymore either. You can just do this one. This satisfies both. And then so if this difference, this new value and t, if there is something in that set, if this difference in this value in t, take that difference, and you check in your sliding window, and you say, okay, there is something that this is not greater than. In other words, there's some value that's larger than this difference. Call it x. So if there's some x greater than, so v minus t, that means x greater than v minus t implies x plus t is greater than v. Or t is greater than the difference between, right, x and v, which is what you're looking for, right? And it's got to be, t is greater than or equal to. Greater than or equal to. Which I think lower bound gives you greater than or equal to. What's confusing about that is the negation, the other direction. Kind of surprised by this, that this works out. But I guess it makes sense because the values are sorted already. So in the window, so you only need to do one difference. I don't know, that's kind of weird. I would kind of expect, yeah, that's pretty interesting. I don't know why. I kind of have to think about this for a while to kind of understand why this works. But this is a very interesting solution. And yeah, so then if you find something that satisfies the condition in the window, and then you check the absolute difference, then you technically don't even need this part, actually, I believe. Oh, you know what? No. No, it shouldn't matter. You don't even need this. I could be wrong. I don't think you even need this. As long as you find something, then you return true. This is by definition. This is true. Yeah. Pretty interesting approach. Yeah, that's really interesting. So I was thinking maybe you could have a sliding window like that on the left side. Wow, that's I like this approach. This is really good. And then obviously you delete sort of the left side of the sliding window as you go to make sure that it's at most size k. And that's actually also why he has this line here, is that he wants to use this as a nifty kind of way to sort of find the other side of the array, sort of symmetric side. Sort of, this is like if you have the kth element from the left, this will give you the kth element from the right, or vice versa. Excuse me, this function. Really interesting solution. Yeah, a lot better than what I did. I kind of mucked up the question a bit. Didn't realize the sliding window is what you wanted to use. That's okay. I mean, what are you going to do? Sometimes you miss it. Sometimes you don't realize it. But that's pretty good. It's a pretty good solution. You know what I want to try? I actually do want to try. I do want to try the. I want to try this without the second condition. Let me do that. Let's give it a shot. Let me save what I did first. I don't lose that. I don't want to plagiarize. I just want to test it. Okay. All right. Does that work? All right. Let's give it a shot. Okay. And then what I want to do is remove this. I think this still works even if you remove this, which is a little bit. It's kind of interesting. Wait, what's wrong? What is the issue? Oh. I think it's still true. Wrong answer. Really? You do need that, huh? Huh. Why though? I really gotta think about this then. Yeah, that's what I'm saying. I don't think I fully understand this solution. I wouldn't have come up with this then. Definitely not. If I can't understand it after looking at it. Let me jot this down. So you have x. There's some x such that x greater than or equal to sort of num n of I. We'll call it or we'll call it v minus t, which implies that t is greater than or equal to v minus x, right? Now it doesn't suggest that t is greater than or equal to x minus v. That I think that's kind of what v minus x, x minus v. That's kind of what I was trying to say, is that so v minus x is less than or equal to t. However, it may be the case that that I don't really get. This position is x, right? This is x minus v. Absolute value of x minus v is less than or equal to t. I think what he's suggesting is that it's got to be both. It's got to be v minus x is got to be less than or equal to t, and x minus v is less than or equal to t. No, it's just the absolute value. I think this is just an extra check. I don't know. I don't really get it. I don't really understand. Sort of x minus v absolute value less than or equal to t implies that x minus v is it's either x minus v is less than or equal to t, or v minus x is less than or equal to t, which could be rewritten. I think that's the thing, is you want to rewrite this as an and rather than an or. It's either x minus v is less than or equal to t, and v minus x is greater than or equal to negative t, or the other way around is v minus x is less than or equal to t, and x minus v is greater than or equal to negative t. And I think the issue is x minus v being less than or equal to t automatically implies that it's greater than or equal to negative t. I want to say these are equivalent to each other, something like that. Or something like that. Like I'm missing something here. Yeah, being greater than or equal to negative t doesn't necessarily mean you're less than or equal to t. And these aren't necessarily, there's not necessarily any equivalence between any of these. It's just you either have both of these or both of those. These are equivalent, actually. These are the same statement. These are the same. There is a relationship. These are the same, right? X minus v less than or equal to t implies v minus x greater than or equal to negative t. And which then means that v minus x, if it's greater than or equal to negative t, what's its relationship to t? Well, I don't know, I guess. Oh, it's confusing. Oops. X minus v is less than or equal to t, and v minus x is greater than or equal to negative t. What is the relationship? Is v minus x less than or equal to t as well? Right, I guess that's what I want to ask. Something like that. Basically, I don't. I'm missing something here. So x is less than or equal to t minus v. So the question, what this looks up is x minus t. There's some x such that x is greater than or equal to v minus t. Actually, starting from v minus t, we want x is greater than or equal to v minus t. If this even exists, what I was suggesting, if this even exists, then you have x minus v is less than or equal to negative t. Or alternatively, v minus x is greater than or equal to t. Which these are equivalent. Okay, however, that doesn't necessarily mean the absolute value is satisfied, right? Come on, man. What? Wait a second. What? This is not what we want. We actually want the opposite thing. We want v minus x is less than or equal to t, or x minus v is less than or equal to t. I don't understand. My brain is turning to mush with this. Let me delete all that. Let's try again. Yeah, I'm not getting it. I'm struggling. I'm struggling, man. All right, so this set is the trailing window of values, right? All just a bunch of values to the left. This is the value itself minus t. Now what we're looking for is sort of a minus b is less than or equal to t, or b minus a is less than or equal to t. Right? We're looking for these things. Now, a minus b is less than or equal to t, or b minus a is less than or equal to t. What we have is some v minus t, and we're searching through the set to find the smallest value that's in the sliding window, that's what's sorted, that's larger, greater than or equal to, so x that's greater than or equal to this x that's greater than or equal to this v minus t, right? And so now if you take x minus v, that means it's greater than or equal to negative t, which is to say, which is equivalent to, if you negate both sides and flip the or just even, yeah, well, yeah, negate both sides and flip the sign. Alternatively, add t, add v, subtract x. Right, if you add t to the left, and then add v and subtract x, right, that's v minus x is less than or equal to t. Which is actually what we're looking for, right? Okay. And this is the smallest possible value where this is true. Okay. Now my contention is I'm thinking that this should just be, we should just be done at this point, right? Like this should be sufficient. And the other condition, right, the other possibility is if you had, so if you had x is greater than or equal to v plus t, and then you would say that would give you oops. This would give you x minus v is greater than or equal to t. We want, actually I think, no, I don't think that's the other possibility. I don't even know what this gives us. I don't know. It's just so confusing. I don't even know. It's not necessary at all. He shows that. I guess I could show that too, but this is did I do this wrong? Oh man. Okay, let's add t and subtract x. There we go. So v minus x is less than or equal to t. Okay. If you have x is greater than or equal to v plus t, then you still want something less than or equal to t. You want, I don't know, like x minus v is greater than or equal to t. This is useless, and this doesn't mean anything. This is not what we're looking for at all. I don't even know what that even, why that even matters. I don't know. He threw it in there as if it mattered, but I don't think it's relevant. Really, I think it should be x greater than or equal to t minus v would be the other one, right? And then you could do, or is that right? I don't know. I don't know. I'm so confused. I don't know. We can just focus on this one though. So my thinking though is that if this even exists, this v minus x less than or equal to t even exists. Oh, I know why. because you need v minus x to be the negation of v minus x to be, I know why. Yes. Okay, I get it. So v minus x is less than or equal to t is what you're looking for. You need that. However, the reason why you need the second condition is because v minus x could be actually less than negative t, right? And if v minus x is less than, which is, so it could be less than or equal to t, but also less than negative t, which would make it the absolute value would actually then be greater than t, right? That's why you have to do it this way. Okay, I got it. That makes sense now. That makes sense now. There's no reason to do it any other way, I think, because like this is just necessary to begin with. Because it's like symmetric, the values that you're looking for as you're searching, they're going to end up, the reverse pairs are going to be checked anyway. So you can always just check for less than t. They're always going to be checked against each other. I think so. Or am I wrong about that? Well, if you have v minus x, if all of the values that you look at, if you subtract t from v and it's larger than everything in the window, right? Then the difference between v and the values that you're considering thing about this is confusing is this is really interesting too. Okay. There's like a lot going on here, kind of. The value that's too negative, right? So if v minus x is greater than t to begin with, then the absolute value of v minus x is going to be greater than t anyway. X is sorted from smallest to largest, right? So and you're looking for the value that's greater than or equal to this difference. So that means if you don't find anything in the array if you don't find anything in the array that's greater than or equal to this difference, that implies for every value of x, this is not true. So for every value of x, v minus x is greater than t. So if you take the absolute value of v minus x, that's always going to be greater than t, right? Just by definition. And so it must be something in this array, or rather that end condition is yeah, that would automatically throw you out. Now, knowing that if there is a value where the absolute value is sufficient, excuse me, that it would have to be in this array. Right, well if it's true, then this condition that's exactly the condition you're looking for. And this has to be true because it's either this one is less than or equal to t, or the negation of this is less than or equal to t. Which is just, it's either v minus x or x minus v. And the reason why this is already automatically Really, this is the problem, is that we didn't check. We have to check this other condition is true. That's really it. You need these two conditions are true. And for every possible v and x, you're going to loop through every possible v and x. You need to have both of these. That's what it means to be absolute value of v minus x to be less than or equal to t. Implies that v minus x is less than or equal to t, and bounded above by negative t. So actually, you could even modify this then to say v minus x is greater than or equal to negative t, instead of using absolute value. So x is this position 1, v minus x, see if I got this right, is got to be greater than or equal to negative t. Can I do negative t? Yeah. Yeah. Slight variation, but yeah, that's really what you're checking. That's really why you do this extra absolute value check. You're really just looking to make sure that this other part of the condition is true. But there's like some stuff going on here, you know. There's like it's like a little more complicated than that. It's a little more to it than that. I think that's it, man. I think that's just always the case. Like you're checking every possible v minus x pair, and you need to have less than or equal to t and greater than or equal to negative t. That's the definition of the absolute. The absolute. What do they call that? The absolute. Absolute value of a difference. Yeah, absolute difference. So, by the way, if this is true, this is logically equivalent to this. So that's kind of where this all plays into effect, where this makes sense, is because by definition you'll have, yeah, that's why you don't need to check symmetrically or anything like that. That's why you only need to check for this first condition, and then also for the other condition. And obviously nothing in the window will work if this isn't true, right? If this goes right over the end, nothing in the window has this property in the first place. And then now you're also, now here's the thing, with the sorted set, you found the value, the smallest value that satisfies this condition, right? And the reason why you want the smallest value that satisfies this condition is you want that value to be greater than or equal to negative t. Or rather, yeah. You found the smallest value of x that satisfies. So this is actually the largest value of v minus x. So you want the largest possible value you can get. So all the other possible values would be smaller, and the largest value has to be greater than or equal to negative t. That's why. That's why you want to use the set. Really interesting. That's why you only need to do one check at the end. Really interesting solution. I like that solution a lot. I'm kind of confounded though, because apparently my solution was faster than his and used less memory somehow. I don't really know how that's possible. Oh, it's faster and uses less memory because this long. That's why. Yeah, because this. Okay, that's kind of interesting. My really complicated, funky, and really involved solution is actually faster than his, because you don't have to do these checks. Yeah, I wonder. I'm pretty sure you can modify this to int and it still works. Yeah, let's give it a shot. Actually, these test cases are, that's okay, that's fine, we don't need to. Oh, no, no kidding. No, it doesn't work. So you do need to, it also doesn't need to be a long, it could just be a long. I'm not sure if it matters. Yeah, it's still slower. That's pretty interesting. So the only reason why this is slightly less efficient than what I did is because what I did allows you to only modify. You only have to, in one spot, you have to upgrade to a long, whereas the set is always a set of long values, which doesn't really make sense. So pretty interesting. So my solution was actually faster and used less memory, just because you didn't have to use larger integers in too many extra places, even though my solution was so much more long-winded. Nums of I minus t. I gotta think about that. I need to go get food also. Nums of I minus t. We need, what do we do? The thing about that is yes, t could be large enough such that the difference between nums and t gives you something that's a long. And this lower bound, when you check over the set, oh, that's very interesting. That is very interesting. How did I do it? Oh, because the only set that I used was a set of the indices. And I performed a check over the, yeah, I performed a check over the indices rather than a check over the values themselves. Pretty interesting. Yeah, I sorted the set first, and then I created tuples of values and indices, sorted on the values, and then created a sliding window to the right side of the indices, and then did a lower bound check on the indices. Because the values to the right would always be the sort of closest, and I actually used t as the limiting factor for the window. So actually, I built the window the other way. He built the window using the indices. I actually built the window using the values, the difference in the values. Yeah, and then obviously if there's any values, or the difference in the indices. Yeah, right. So the any values with the difference in the indices that are possible, if there are any, the ones that are closest, if either of those closest indices are in range, then that's sufficient. Pretty interesting. I actually really like my solution. Mine's pretty good. It's different approach. This is way more concise, but yeah, technically mine is a little more efficient because you don't have to use the set like this for the longs. Mine's a little more involved too. It takes a few more steps. So pretty neat. Yeah, I like that. That was good. I mean, I didn't see it. I didn't see it to use the sliding window. I kind of really screwed this problem up. I kind of like looked at it a bunch of different ways and kind of went all over the place. But eventually got there, I guess. So yeah, that'll be it for this question. Thank you for watching. I appreciate it. Talk to you soon. I'll be gonna end the stream here and then go get some food and then come back and probably do another problem. Let's try a stream maybe probably one more problem before bed. Probably one more. So yeah, I'll get going here. So thanks again. Thank you again. Take care.